All right, let's look at 3.6. And 3.6 is our last unit in the Unit 3. It concludes by looking at higher order derivatives, which we've done a little bit of. We have talked about second derivatives. So it says if f is a differentiable function, then f prime is also a differentiable function. What does that say to you? Well, it means if I start with a function that's differentiable, then, and it's a function, then if I take its derivative, the result will also be a function. Therefore, we can consider the derivative of f prime denoted as f double prime of x. Therefore, we can consider the derivative of f prime. So the derivative of the derivative gives us f double prime of x. This new function, f double prime, is called the second derivative because it is the derivative of the derivative. So it's a rate of change of the rate of change, if you want to think of it in slopes. There's some notation that comes along with this. And so we've got Newton's notation, y prime, y double prime for second derivative, y triple prime for third derivative. Oh yeah, we can just keep taking derivatives. And then it starts getting a little messy doing all those tick marks. So usually at the third derivative or fourth derivative, you just start writing it in parentheses, superscript it. So I get y, the fifth derivative, ooh, messing up, fifth derivative, and y sixth derivative. Oh, nth derivative. We'll put an n in there. How about that? I was just thinking I might try to move this up, then my hand won't rest on all the tools. Lagrange's notation, his second derivative also could use these tick marks. Third derivative, if you'd rather for the third, you could put it in parentheses. F of the fourth in parentheses, that's the fourth derivative. Fifth derivative with parentheses of x. Nth derivative of x. We will use these heavily in Calc 2 as well. Leibniz's notation, well, this is where it starts getting a little interesting. We've seen the second derivative written out when we did implicit differentiation, section 3.3, I think. And it's d squared y over dx squared. Because what you're doing is taking the derivative with respect to x of dy dx. So you can see how it's d times d gets me a d squared. You think of it in that terms, I think it helps. The derivative of the derivative. And dx times dx gives me a dx squared. Triple, well, these are going to be just all the same now in the same kind of fashion as that second derivative. So I get d raised to the third of y dx squared, or cubed, d4x over d, that should have been a y, over dx to the fourth, d5y over dx5, and then finally the nth derivative, whatever derivative you want it to be, dn of y over dx raised to the n. Okay, so hopefully you can recognize those when you see them. Example 1 has us walk through taking derivative after derivative after derivative. That won't be too hard, especially when you start with polynomial. Those are actually kind of the nicest ones. So I'm going to have the first derivative, 6x to the fifth minus 8x to the third plus 10x minus 3. Power rule all over the place there. Next, we want to get to second derivative. I have the first, so I can just take another derivative. 30x to the fourth minus 24x to the second plus 10. Another term fell by the wayside, right? There we lost a term. Now we lost that term. Third derivative. Well, use the second and take a new derivative. 120x to the third minus 48x. Another derivative. Yep, I can get a fourth derivative out of this, so I'm at 360x squared minus 48 Looks like I could go to the fifth derivative, 720x. I go to the sixth derivative, 720. And then the seventh derivative, I would finally zero out, and I could no longer take any more derivatives. So yeah, I could get a lot of derivatives out of that. On the right-hand side, we have some mixed functions going on there, and they want us to get to the second derivative. So I'm going to go 6x squared, that's just power rule. Derivative of cosine is negative sine. I got negative negative, so I'm going to put down a positive sine x. Derivative of natural log, that's an easy one. It's 1 over x, right? And then the last one, e to the 4x, is going to be a little chain rule. We know the derivative of e to the x is itself multiplied by the derivative of u, so that would be a 4. So I'm going to squeeze that right in front of there. Now let's go take a new derivative. Get to the third derivative. We're at 12x. Derivative of sine is cosine. This is the only one that's tricky. In my head, I'm thinking it's x to the negative 1. So I'm going to have minus x, subtract a power, and I'm at negative 2 power, minus 4e to the 4x. Uh-oh. It's slowing down. 4x there. And the derivative of e to the 4x is e to the 4x times a new 4. So I get multiplied by a new 4. And this will give me a 12x plus cosine x, I apologize, minus 1 over x squared minus 16 e to the 4x. Got it. So taking higher order derivatives, not too tough. I'm going to erase some of this ink so we don't have it all trying to be saved. And let's erase that. All right, on to this next one. What is it asking us? I gotta flip the page. Function notation. Oh, we're going to get into particle motion. Good. It's about time. Just as you can obtain a velocity function from differentiating a position function, you can obtain an acceleration function by differentiating the velocity function. There were three key phrases that I picked up in there that sounded somewhat new. Position function, velocity function, and acceleration function, all having to do with particle motion. So when I start out with an original function like s of t, in physics it's often referred to as x of t. In AP Calc we'll use both. This is known as the position function. It describes the position of the particle along a line. That line could be horizontal or it could be a vertical number line. So it just tells us where the particle's at. It's at 3. Maybe that's 3 feet, right, to the right. If it were negative 3, it'd be 3 feet to the left of the origin. Then if I take a derivative of the position function, I get velocity. So this is the velocity function, which describes the rate of change of position, right? How fast is something going? It represents how fast a particle is moving and the direction that it's moving. So it actually tells us two pieces of information. The positive and negative describe the direction. So I'm just going to put a plus minus there. Plus means it's moving to the right or upwards. Negative can be interpreted as leftward movement or downward. And then the speed, of course, is the fastness. And now if I take another derivative off of position, which I'd be at the second derivative, which if I take a derivative of velocity would be the first derivative of velocity, I get to acceleration. So acceleration is the second derivative from position, or it's a rate of change of velocity, the first derivative from the velocity function. Okay, so acceleration is the rate of change in velocity. I should put in what the units are. Let's just put some standard units in here. If I had meters and seconds, this would be meters. Velocity would be meters per second. And then the rate of change would be meters per second squared. Okay, those are typical units. Of course, we could have feet, we could have miles, all of that fun thing. Hours. Example 2, let's revisit a scenario from the first week of class. Suppose a ball is dropped from the top story of the famous building in Dubai, 2,717 feet from the ground. The position equation that depicts the height in S of t in feet the ball is from the ground at time t in seconds is modeled by this function S of t. Remember, that is our position function. Let's even make a note of that. This is our position function. It gives me the height of the ball at any particular time t, which is in seconds. Compute the velocity of the ball at time 5. Well, velocity is a rate of change of position, right? So velocity, v of t, equals s prime of t. I'm just showing my knowledge there that I need to take a derivative of s of t. That'll give me negative, darn it. Negative 32t minus 10. Ooh, that got really nice and simple, didn't it? Let's evaluate it at 5. And that would give me negative 32 times 5, whatever that is, minus 10. 150, 160. I think this is going to come around negative 170 feet. Yep, feet and seconds. Feet per second. We want to get that label in there. Compute the acceleration of the ball at time t equals 5. So I need to go one more derivative. So I'm going to get to acceleration by taking the derivative of my velocity function, which is really taking the second derivative, I'll write it in here, second derivative of the position function. And I'm looking back here. I need to take that derivative. That's going to give me negative 32. So at 5, well, at 5, it's still going to stay 32, isn't it? Negative 32 feet per second squared. Does anybody recognize this, especially if you're in physics right now? That's the effect of gravity, isn't it? Yep, this is acceleration due to gravity. When will the ball hit the ground? And then we got a hint. It says, what will be the position of the ball when it hits the ground? The position would be at 0, wouldn't it? So when will it hit the ground? I'm going to take the position function and set it equal to 0 and then solve that. So I'm going to get negative 16 t squared minus 10t plus 2717 and set it equal to 0. To solve that one, I don't know if it's very factorable. I think what I'm going to do is put the equation in my calculator and get the 0. I'm going to find the 0 of my function in the calculator. Okay, so I'm going to pause because I got to get my calculator open. Okay, so I can't open the calculator on my home computer. It's not available right now. So I did my calculator and found out I have a graph that looks like this. This would be 2717 at time 0, right? We were at the top of the building. Dropping it down, I'm looking for where did it cross the x-axis there, or the t-axis. And my answer came up to be t equals 12.72246 seconds. So what will the position of the ball be? That doesn't answer the position question, does it? I need to take that time that it took for it to hit 0, plug it into the position function. So this will be a second step, and that's to evaluate s of 12.72246 into my position function and get an answer. I will do that real quick. Store, I need to x store in alpha a. All right, and then I need to evaluate my function y1 at my a. Oh, obviously it's 0. I don't know what I was thinking there. I was getting twisted. We don't need to. We know this is equal to 0 because that's what we were setting up to be. It was a time question, I guess. I was reading the second part. When will the ball hit? At t equals 12.722 seconds. AP Calc, we need 3 decimal places. Part D, what will the velocity of the ball be at impact? This is what we need to do. So we need to know the time it takes the ball to travel until it hits the ground, which we got on our previous answer. So we'll substitute that into the velocity equation. All right. And my velocity equation was v of t equals, I forget it, negative 32t minus 10. All right, so we want to evaluate that at, really I want this. I need a lot of decimal places so that I can be accurate to 3. And I'm going to pop in negative 32t minus 10 into a y2 equation so that I can evaluate y2 at my stored value of alpha a. I'm getting, you see what you get, but I get v evaluated at 12.722 is equal to negative 417.119 feet per second is how fast it was going when it finally hit the ground. The negative tells me this was a downward motion. Nice. It should be traveling down, shouldn't it? We dropped it from the height of the building. Okay, so you have some particle motion questions in the worksheet. Follow that guideline. That should help you. I'm going to go ahead and pass on this. Second derivative implicit, we've done those before. Let me finish up by doing example 4. So x squared plus y squared equals 100. We want to get to the second derivative. Oh, this is the same problem we've done prior in our work. One of the lessons, 2x plus 2y dy dx, because it's implicit, equals 0. Solve for dy dx, and you'll find out that dy dx equals, subtract 2x, that's negative 2x, divide by 2y, you're going to get negative x over y. Now, we need to get to the second derivative, so I take and do the quotient rule, so d squared y over dx squared, and I'm going to get negative 1 times y minus negative x times dy dx over y squared, right? Derivative of the bottom, which was dy dx, times the top, which was negative x. This will give me a plus in here. Now, if I wanted this expressed in x and y, then I need to replace this. And that, if you remember from when we did implicit, replace with the dy dx, which was equal to negative x over y. So I'm going to get the second derivative to be negative y plus x times negative x over y all over y squared. That's going to give me a negative y minus x squared over y. I'm going to have a fraction within a fraction, darn it. We should make this a less complicated fraction. So to do that, we need to have this guy with the same denominator as our other part in the numerator. I can't just simply slap a y down there, but I can multiply by y over y, can I? Because y over y is like multiplying by 1. So I get negative y squared minus x squared over that common y over the other y squared. Now, how do I join that together? Because we're still a complex fraction. These y's join up together, because remember, this is like a y squared over 1. Multiply by that, multiply by the reciprocal of that, I get 1 over y squared times that y, gets me a y cubed. And this is looking like negative y squared minus x squared over y cubed. There is our second derivative fully expressed in x and y's. All we need to do is evaluate it at 6/8. Throw your 6/8 in there. I think the answer was negative 25 over 128, if I remember right. Higher order derivatives. It says find what? Find the 23rd derivative. Well, I don't really want to do 23 derivatives, but I do see that this one will eventually tap out at 0 after about the 4th derivative. So that won't go on and on and on. Sine, though, derivative of sine continues to go on and on and on, doesn't it? So let's just start this out. This will be fun. F prime of x, 3x squared plus 5 cosine of x. Take another derivative. F double prime of x would equal 6x minus 5 sine of x. Take another derivative. We're on to the third derivative. Got a ways to go till we get to 23. We get 6 minus derivative of sine is positive cosine, so I have minus 5 cosine of x. Take another derivative. We're on the 4th derivative of x. Ooh, it did tap out. That went to 0. That's not going to be a player anymore, is it? And I'll have derivative of cosine is negative, so I'm going to end up with a positive, whoops, right, please. A positive, come on, you can do it. A positive 5 cosine x. Oh, I'm sorry, 5 sine x. I don't know what happened. Anyway, I need to continue thinking that through all the way till I get to the 23rd derivative. But what I could do is just start counting them off. So this would be the 23rd, or the 4th derivative. Then I could start back up at the top of my derivative list. That would be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Anyway, the answer, my friends, comes out to be negative 5 cosine x. See if you can get there by walking through those various derivatives. The trig derivative of sine and cosine go in a pattern of 4, kind of like i's do. So that makes it a little easier to remember. All right, that's all I have for you.